Hello. In this lecture, we will look at Lagrange's equations of the first kind. We have discussed in our previous lectures that the Newtonian scheme requires that we have complete knowledge of all forces acting on a system. Say we have a single particle and we would like to describe its motion, then the equation of motion is given by mass times acceleration is equal to the total force. Now this total force is basically is usually composed of the external force as well as forces coming from the constraints acting on the system. So one needs to have a complete knowledge of the forces coming from the constraint, and this is where we often run into trouble because often we know the constraint equations, but we do not know how the forces look like. This is where Lagrange's equations of the first kind are very helpful. I mean, they tell us how to construct the constraint forces given the constraint relations. So, we consider this particle again, and now let us suppose that apart from an external force, we also have constraint forces of constraint acting on the particle, and there are two constraints. Let's say one is a function of position and time, and this is, of course, we know this is a holonomic constraint. And let us suppose we also have a non-holonomic constraint where it's a function of position, velocity, and time, and it is not integrable. So, how do we find out the constraint forces now? All right. We look at the second constraint first, the non-holonomic constraint. This is a function of position, velocity, and time. So, if this constraint restricts the position, velocity, and time of the particle, then it must have some clue about how the acceleration of the particle is constrained. Say, for example, we take the total time derivative of this function. And what do we get? If we use chain rule, then it is straightforward. Del g to del r times the velocity, then del g to del r dot times the acceleration, and of course we have the explicit time derivative. Now look at the first term here. This bracketed term could be a function of position, velocity, and time. It's not a function of acceleration. There are no r double dot in this expression. And this is, of course, velocity. And the del j to del r dot, this could also be function of position, velocity, and time. It's not a function of acceleration. And similarly, explicit derivative of time, explicit derivative with respect to time of g2 does not contain any acceleration. So basically, this particular term and shows us this. The constraint has something to say about the acceleration of the particle. Now, this is a vector, of course, a vector coming from the constraint, and this is acceleration of the particle. We can break it into two parts. One is a parallel component to this vector and a perpendicular component to this vector. And it is, you can see, the perpendicular component of the vector, the perpendicular component will not contribute because the dot product of two orthogonal vectors is 0. So essentially, the part of the acceleration parallel to this vector is influenced by the constraint, or in other words, the constraint has something to say about the acceleration along this direction, the direction given by this vector. So it is clear, if a vector quantity dictates that how the acceleration should be along that direction, so a force must be acting along that direction. So that was the argument originally proposed, that maybe we have a force acting in this direction and that influences the acceleration. As such, we may say that force coming from this particular constraint is proportional to del G del R dot, and we can say it might be equal to, if we multiply by a proportionality constant whose value we do not know yet, lambda 2 del G 2 del R dot. So this is our force. Alright. So we got some kind of a force from the non-holonomic constraint, and we can get the similar one from the holonomic constraint, but in this case we have to take the time derivative twice. Let's take it one time, and from the chain rule we have simple, and if we take the total derivative once more, then we have now this term del G1 del R could be a function of position and time, so its total derivative can at the most give us velocity but not acceleration. And similarly, the last term del G1 del T here, it could be a function of position and velocity, so its total derivative will also give us position and time, so its total derivative will give us at the most velocity. But here, so here we have the acceleration appearing in this expression only once. By the way, both the expressions are equal to 0, of course. So here too we have a similar situation. This is a vector, and this vector dictates that acceleration along this vector will appear in this constraint relation. Acceleration perpendicular to the vector that does not get influenced by G1. So as such, force from this particular constraint would be proportional to del G1 del R and would be equal to some unknown proportionality constant times del G1 del R. So now we have a good situation in the sense that we can write down the equation of motion now, mass times acceleration, and we have the external force acting on it, and then there are two constraint forces, one coming from the holonomic constraint and the other coming from the non-holonomic constraint. Remember, for the non-holonomic constraint we are taking the partial derivative with respect to velocity, and for the holonomic constraint we are taking the partial derivative with respect to the position. That's it. So basically, given the constraint relation, we can have some estimate about the force. But then there are unknown quantities. There are two unknown quantity, and moreover, this is an equation of R. It involves the time derivative of R. So essentially, the three components of R are unknown. So total number of unknowns are 3 for 3 components of R, and then 1 for each for lambda 1 and lambda 2. So we have 5 unknowns, and we also have 5 equations, fortunately, simply because there are 3 equations here for this equation is in a vector notation. It involves three separate equations for x, y, z or r theta phi, and then we have two constraint relation g1 and g2. So total 5 equation and 5 unknown, that matches beautifully. So this is a solvable problem. That was Lagrange's idea. Now this can easily be extended to a multi-particle system. Suppose instead of one particle we have many particles and their position coordinates are all given by, let's say we have n particle. Then the argument put forward above, it can be applied to say jth particle. If that happens, then for jth particle we should be able to write, if we have two constraints, if we have just two constraint, then the external force acting on the jth particle, then we have lambda 1 del g1 del rj minus lambda 2 del g2 del r. Here we assumed that these two constraints that we have, they are holonomic and non-holonomic constraints, and they involve the position coordinate or velocity coordinate of jth particle. It may not have that coordinate. In that case, these derivatives will simply vanish. The situation would be very simple for that particular particle. Now, if we have say one more constraint, then how would it get modified? I mean, suppose we have one more holonomic constraint, then it would be simply like the derivative is with respect to position. So in general, if we have many constraints, many constraint relations, say k1 number of holonomic constraint and k2 number of non-holonomic constraint, we can write it in this form: mass times acceleration of the jth particle. I mean, I am assuming all particles are of equal mass, but if we have particles of different mass, we may have to add mj, jth particle, and then one undetermined multiplier for each type of constraint. So we will have and m is running from 1 to k1, and then in this sum m is running from 1 to k2. So overall this is how it would look like, and we will remember that this is the general form of Lagrange's equations of the first kind, and it's quite useful because given constraint relations, now we have no problem in constructing the equation of motion. But then solving that equation of motion is another story. Sometimes it could be complicated, but at least we do not have to make cases about which way the constraint forces are acting and what are their magnitudes. So that is definitely a big advantage. Now let us try to solve one problem using this Lagrange's equation of the first kind. So the example that we choose is, let's say, a simple example: a particle moving on a circle, and there are no external force. I mean, it could be a particle moving in a plane along a circle. It's constrained to move on a circle. Okay, so the constraint relation is quite straightforward. It's a function of x and y, and precise form is x square plus y square is equal to r square. Equation of a circle after all. And we have of course chosen the origin here for convenience, And so what would be the constraint force? I mean, assuming lambda be the undetermined multiplier, then it's simple del G del R. And this undetermined multiplier, also known as Lagrange's undetermined multipliers, we'll know more about these undetermined multipliers in later lectures, but let's go ahead with this. So del R is, as we described earlier, it's simply, we are taking gradient, we are keeping the problem confined in 2D. We are not going beyond that. So this will give us, I mean, we can also write the constraint equation as this. Then we will have, after taking the derivatives, twice lambda x I caps plus, that's it. So this is our constraint force. So the equation of motion is simple, m r double dot, which in x and y, x double dot, y double dot with their respective unit vectors. Then this constraint force, remember there is no other external force. That's our equation of motion. Equation of motion. And this equation of motion could be broken down into two separate equations, one for x, one for y. And of course there is a third constraint equation. So total number of equations is 3. And we have 3 unknowns, x, y and lambda. Now how do we solve it? Well, the trick is to use the constraint relation. So one easy way of removing x and y using the constraint relation is to assume a parametric form, say x equal to r cosine theta and y equal to r sine theta. This gives us x dot to be minus r sine theta theta dot, and that gives us x double dot to be and for similarly for y we have and for y double dot we have right. So now we substitute these expressions along with the form of x and y in our first two equations, this one and this one. So what do we get? We have and we call it equation 1, and then the second equation. Now to get an equation of theta double dot, we multiply the first equation by sine theta and subtract from that the second equation multiplied by cosine theta. That cancels the first equation, and also it cancels, I mean first term, and it also cancels the last term. And finally we have now this equation tells us that theta double dot is 0, that means theta dot is constant. Of course it's quite expected simply because there is no external forces acting on the particle. So if the particle is moving along the circle, its speed should be constant. And what about the lambda, constraint force and all? So for that we do multiply first equation by cosine theta and then add the second equation after multiplying it by sine theta, and that gives us, I think there was a small mistake of the sign here. Yes, okay. So after all, the sign must be opposite, otherwise the subtraction will not add up this. Okay. Now if we do this, then what do we get? What we get is something like and that gives us lambda to be equal to m theta dot square by 2. So therefore the constraint force, which was we go back, here is the constraint force 2 lambda xi caps plus yj caps. So that would be 2 m theta dot square by 2, the 2 factor cancels, and xi caps plus yj caps, which is also is basically the r vector. And we also should not forget the negative sign. The negative sign is here. So that means for this particle, the constraint force is inward along the radial vector, but inward. Of course, that negative sign means that. So what does the constraint force do? It's an inward force, so it's making the particle go in a circle. So remember, there is no external force. The only force is the constraint force, and that is responsible for the change in velocity. The velocity is constantly changing. The speed is fixed, which is theta dot, but r theta dot to be correct. But its direction is constantly changing, so it's essentially accelerating, and that acceleration is being provided by the constraint force. Now what if we go to a rotating frame of theta dot? Well, in the rotating frame there would be a pseudo force, the centrifugal force, and this centrifugal force would be nicely balanced by the constraint force. So the net force on the particle would be 0 in that frame, and the particle will remain static. After all, we are rotating with theta dot, so we will not see particle going anywhere. So this is this is an example of Lagrange's equation of first kind, and it kind of shows the effectiveness of the strategy. Solving equations it's a cumbersome business, but at least we can write down the equations. Thank you.